All right, so we are in section 15.5. We're going to talk a little bit about surfaces. So we'll talk about parametric surfaces today, and tomorrow do a little bit with parametric surfaces. And then we're going to talk about surface integrals. So we are moving from line integrals into surface integrals, and the surface integrals are really what we're interested in. What I did with Green's theorem at the end of the talk on Friday, where we talked about the divergence and the curl, summing the divergence and the curl on the region. We're going to do that in 3 dimensions, and that's really what we're trying to get to. All right, so we've worked with parametric equations of curves, and both as parametric equations and with vector valued equations, vector valued functions. So we're going to do a similar thing with surfaces. For curves, we usually used a single parameter, like t or theta, to parameterize. For surfaces, we're going to have two variables. Our parametric equation is going to be functions of 2 variables. Now let's just kind of do a little bit of review, or just clarifying of terms. So if we were talking about curves, we worked with equations in a couple of different forms. We had an explicit form, where we have y equals some function of x. And our implicit form we have some function of x and y, and I'll use a capital F to make a distinction here. Some function of x and y equals 0. So when we had to differentiate implicitly or something like that, our equations were in this form, some function of x and y equals 0. And then we worked with parametric or vector forms of equations for curves, where we had some r of t equals f of t I plus g of tj. And parametric and vector form are essentially the same. The parametric form is just the components of our vector form. So with surfaces, we've worked with equations of surfaces a little bit. We have a similar thing. Our explicit form of the equation for a surface, and we had a discussion a little bit ago about what this was telling us when we were trying to do a surface integral. Our explicit form for a surface is z equals some function of x and y. And we decided that z was our height above the xy plane if we're looking at it that way. Our implicit form for a surface is some function of x, y, and z equals 0. And we worked with this implicit form when we have a surface represented implicitly like this. If we take the gradient of our function, we get a normal vector to the surface. So that's one example of when we use this implicit form. Now, today we're going to talk about the parametric form of a surface. And it's just a different way of representing a surface that has advantages in certain situations. So our parametric form of a surface, we use the variables u and v normally. R of u and v is some function of u and v I plus some other function of u and v. So we have these component functions. We have these component functions, and we turn it into a vector equation. And we need our component functions to behave nicely, so f, g, and h are continuous. On some domain in the UV plane. I guess I don't need parentheses around u and v there. So this r of u and v is our parametric equation for our surface. Our f, g, and h are parametric equations for the surface. I'm sorry, R is a parametric surface. We refer to R as a parametric surface, and F, G, and H are parametric equations for the surface. So let's take a look at what we mean by how we work with parametric surfaces. Now we've worked a little bit with a couple of parametric forms of surfaces. We'll get to that in just a second. Just want to emphasize that parametric surfaces representations are not unique. So it's kind of like when we talked about polar equations, polar representations are not unique. When we want to try to sketch or try to visualize a parametric surface, we want to try to eliminate a parameter, just like we did with parametric equations for curves. We want to try to eliminate a parameter, so we look for a relationship between the parameters to come up with a familiar equation. Finding the parametric form of a surface is usually kind of difficult. And exceptions that we've worked with already is if we're working with cylindrical coordinates or spherical coordinates, we have an easy transformation from a rectangular representation to our parametric representation. So we can think of cylindrical coordinates and spherical coordinates as parametric representations of a surface. And if we have a function z, if we have an explicit representation of our surface, z equals f of x, y. So z equals f of x, y. That's another one where it's easy to represent our surface parametrically. Then we can say that r of x and y, we let x and y be our parameters, is just xi plus yj plus f of xy. Okay, so those three cases are ones that we're familiar with already, where we have spherical or cylindrical coordinates, or if we have an explicit form for our surface, then our parametric surface is represented this way. So what I want to do is look at some examples. You have some examples in your book, and we're going to match some surfaces, some parametric representations to their graphs, and then we're going to figure out how we can transfer back and forth between the two forms. So in your books, on page 1105, we're looking at number 1 through 4. We want to match the parametric surface with its graph. So our first one, we have r of u and v is ui plus vj plus uvk, and we want to match the equation with its graph. So my advice, or the way we normally go about this, is we want to try to eliminate a parameter. So we want to find a relationship between x, y, and z. So looking at this equation, what relationship can we come up with between x, y, and z? This z equals xy. There we go. So there's going to be our familiar equation. So which graph does that match? So Scotty, we have a couple of D's, and Scotty's saying C. What is if z is a constant? If z is 1, what is xy equals 1 in the xy plane? What kind of curve is that? So if we let z equal a constant, so let's say z equals 1. So xy equals 1. What does that look like? What? Andrew? 1 over x. So it's a hyperbola. These are hyperbolas. So our shape, our surface is going to be made up of a bunch of hyperbolas, right? So which one does that match? That one's going to match C. This one matches C, because we have hyperbolas here. All right, the second one. We have our parametric equation. R of u and v is u cosine v I plus u sine v j plus uk. All right, so what kind of relationship do we see between our parameters here? X and y make a circle. So when you see trig functions like this, think Pythagorean identities. So x squared, I'm going to square x and y. X squared plus y squared equals u squared times cosine squared v plus sine squared v equals u squared. And that equals z squared, right? U squared is z squared equals z squared. So we have x squared plus y squared equals z squared. So what kind of surface is that? Sphere?
Cylinder. It's a cylinder.
Sphere, cylinder. If we look at, so we go back to our surfaces. Ignore the x, so we get z squared equals y squared, or z equals plus or minus y. So we get a line in the yz plane, a line in the xz plane. So this is a cone. This is a cone. So that matches D. All right, number 3. Emily says B for this one. And what makes you say B, Emily? They have sines and cosines. So let's take a look. So we have R of u and v.
Close enough.
Equals, what do we have? 2 cosine v sine u, or cosine u, I, plus 2 cosine v sine u, sine u j, plus 2 sine vk. All right, so we have these sines and cosines. And we just have a sign here on the k component. So let's square the x and y. X squared plus y squared. We get 4 cosine squared v times sine. You believe you got the sine and the cosine, so we get 4 cosine squared v. And z squared equals 4 sine squared v. So x squared plus y squared plus z squared. Right. Equals 4, so we have a sphere. So that's B.
I think the last one's A.
Yeah, we can eliminate that by process of elimination. And that one, again, we could look at, if you square x and y, you get x squared plus y squared equals 16. Doesn't depend on z at all. So you get a cylinder. All right. So if you're trying to visualize a parametric surface, if you're trying to graph a parametric surface, try to eliminate the parameters to come up with a familiar equation. All right, now let's look at a couple of examples where we want to find something similar, where we're going to find the rectangular equations for a couple of parametric surfaces. So let's just look at a couple more of these where we're doing something similar, and then we want to describe the surface. So R of U and V. This is the same as what we were just doing, except we don't have pictures to match with. So we have UI plus VJ plus U over 2. V over 2. Okay. And we want to come up with a rectangular equation for the surface and describe it. So which one of these parameters, which pair of these parameters are we going to try to relate? Right, so we get, looking at these, we get z equals y over 2, or we can write y minus 2z equals 0. What kind of surface is that? A line? In 3 dimensions? It's a plane. This would be a plane. Because we get y equals negative 2z for any x. So this is going to be a plane. Let's look at another one. This is a plane. We have R of U and V. And this time our parametric surface is 2u cosine V plus 2u sine V J plus 1/2 u squared K. So what are we going to do? What do we want to do with, this should be 2u here, sorry, 2u. So what do we want to do with this one? Square x and y. So we get x squared plus y squared equals 4u squared. And that's z divided by 8. So we get, is it z divided by 8? Z times 8. There we go. So x squared plus y squared equals 8z. And what is that surface? A cone? So not a cone, but a paraboloid. Paraboloid. Cones have straight sides. Paraboloids have parabolas for sides. So this is a paraboloid. All right, let's look at one more of these. So r of u and v equals 3 cosine v cosine u I plus 3 cosine v sine u j plus 5 sine uk. All right, so what do we want to do with this one? Square x and y. So x squared plus y squared. We end up with 9 cosine squared v. And this should be a v here. No, I'm sorry. We get cosine. Yeah, 9 cosine squared v. And how does that relate to the z component? It doesn't? How about cosine squared v, how about x squared plus y squared over 9? X squared plus y squared over 9 equals cosine squared v. Z squared over 5 equals, sorry, over 25 equals sine squared v. So we can say x squared plus y squared over 9 plus z squared over 5 equals 1.
It's a ellipse, but in 3D. I don't know how you say it.
And ellipse, but in 3D. So this is an ellipsoid. So kind of a football shape. What was that, Andrew? What was that? For what? Oh. Over 5. Sorry. Over 25. I put 25 here and 5 there. So the question then is, if I make mistakes like that, did I actually make a mistake, or was I trying to see if you were paying attention?
I think you actually were mistaken.
What was that one?
It's not a test. I was just thinking through.
Right.
Making
Sure.
you were paying attention, like-
Well, then when I take a point off, you know I was paying attention, right? All right. Now we're back on page 1105. Let's look at a few more of these, and then we're done. So let's look at number 9 through 12. We have a given equation. We have r of u and v equals u cosine vi plus u sine vj plus u squared k. And we want to see how the equations that they give us vary from this given equation. So first off, before we do these, what is this surface?
Oh, that one. The picture.
So we get, if we square x and y, x squared plus y squared equals z. So what is this? A paraboloid?
Yeah.
So we have a paraboloid. So we know what this looks like. Now the first one, it asks what happens if we have u cosine vi plus u sine vj minus u squared k. What's going to happen to the graph?
Is it gonna flip?
It's going to flip. Yep, flip upside down. Um, let's see, so number 10, it says we have u cosine vi plus u squared j plus u sine vk. How is that going to change? What's that going to change? So our paraboloid here, what? So, right, so Caitlin says it's going to go to the side instead of going up. So our axis is going to be the y-axis instead of the z-axis. That's exactly right. Number 11, we have u cosine v plus u cosine vi plus u sine vj plus, what's changed? Oh, look at so our original equation, we go from 0 less than or equal to u less than or equal to 2, and 0 less than or equal to v less than or equal to 2 pi. On number 11, we go 0 less than or equal to u less than or equal to 3. So this is going to be taller, exactly. Number 12, we have our surface is 4u cosine vi plus 4u sine vj plus u squared k. So our parabola is going to be wider. Let me look at one more example. So you guys did well on this one. I want to go from a rectangular equation to a parametric equation. So, and this follows from the example we just did a little earlier. So we have 4x squared plus y squared equals 16. And we want to express this as a parametric surface. So first, what kind of surface is this? An ellipsoid, right? So, so is this an ellipsoid? So Danny says like this. So it's an elliptical cylinder. So it's an ellipse with a cylinder with elliptical sides. So to represent this as a parametric surface, I'm going to divide each side by 16. So I get x squared over 4 plus y squared over 16 equals 1. And what do we want to do? How do we want to represent this parametrically? Sines and cosines. So let's let x equal 2 cosine u. Y equals 4 sine u. That's just our parameter. We could pick t, we could pick v. And z, how does z change with x and y? So what are we going to pick for z? Well, we said that our cylinder goes along the z-axis. So z can be anything, right?
Yeah.
So we can pick just another parameter. So let's let z equal v. So it doesn't depend on x and y. So we're going to say that our parametric surface is 2 cosine ui plus 4 sine uj plus vk. And that's our parametric surface. Okay? All right. Homework. There you go.